In this case study, I will use the MonolixSuite to analyze and model the pharmacokinetics of alcohol and the effect of guar gum on the PK. The case study will in particular focus on the modeling of inter-occasion variability. The dataset that I am going to model is composed of measurements of concentration of alcohol in blood for 7 individuals who have received a single 10-gram dose of alcohol. The measures were repeated later on another occasion with a dietary additive of guar gum, and these new measures have been recorded with the dosing time of 0, just like the first measurements, without guar gum. Guar gum is also called guaran. It is a polysaccharide extracted from guar beans. As a natural polymer, it may affect the bioavailability of concomitantly administered substances due to its effect on the rate of gastrointestinal transit and gastric emptying. So the goal of this case study is to assess the effect of guar gum on the absorption and bioavailability of alcohol. Let's now see what the data looks like in Datxplore. After loading the dataset, it appears here. All column headers are automatically recognized except the last one. ID contained the subject IDs and time the time in hours. The 2 periods of measurement where the subjects have received or not guar gum in addition to alcohol are distinguished with the column OC, which is automatically recognized as occasion. Y is the alcohol concentration in milligram per liters, and some censored observations for the concentration are indicated with the column sense tagged as censoring. AMT is the amount in milligram. In addition, I use the column diet that I tag as categorical covariate to indicate which occasion corresponds to the addition of guar gum. This column contains 2 strings, no guar for occasion 1 and with guar for occasion 2. I can now accept the data and save the project. And here is the plot of alcohol concentration versus time. I choose a log scale and overlay the dosing time, which can be seen as dashed vertical line when I hover on some curve. It is at time 0. There seems to be a nonlinear elimination for some individuals, but the data might not be sufficient to capture it, so I will try a linear model as a first model. I can visualize the different occasions in several ways. First, like you can see here, hovering on a curve highlights the curve in solid yellow and the curve corresponding to the other occasion from the same subject in dashed yellow. Second, OC is available in the panel Stratify for stratification, along with the covariate diet. And it can be used for splitting, coloring, or filtering. So I can split the plot by OC and color it by ID. With this coloring, each subject occasion is assigned a color with similar color shades for subject occasions corresponding to the same subject. For example, here, occasion 1 of subject 1 and occasion 2 of subject 1. This is useful to compare at a glance the 2 occasions for all subjects. I can see that the inter-individual variability seems mostly reproduced from one occasion to the other. For example, in both occasions, the IDs 1 and 2 have higher concentration levels than other individuals. In general, it seems that concentration levels are slightly higher for the occasion 2. I can confirm this global trend in linear scale. I now choose a coloring by diet. The categories of diet are matched with OC. The category no guar corresponds to OC equals 1 and with guar corresponds to OC equals 2. So some inter-occasion variability seen in the data seems to be explained by the covariate diet. As a first simple analysis, I can check the difference in PK parameters for the 2 occasions with non-compartmental analysis and compartmental analysis in PKanalix. So I open PKanalix and I can directly open the Datxplore project to load the data with the same tagging as in Datxplore, as you can see here. Then I should save this as a PKanalix project. And I'm now going to start with the NCA. In the settings, I choose extravascular administration, linear up-log-down integral method, and I choose to handle censored observations after Tmax as missing. I first have a look at the Check Lambda Z tab. I keep the general rule called adjusted R2. This setting selects for each individual the optimal number of points used in the regression to get the best fit. The plots allow to check the regression. I'm going to show all the IDs. And they could also be used to adjust the selection of points individually, but it is not necessary here. I can already see that the estimated lambda z is going to show some variability between individuals. Then I run the NCA. This computes the PK parameters for each individual. The plot of individual parameters versus covariates is convenient to visualize the variability in the parameters and compare the distributions without and with guar gum. I'm going to select, for example, the AUC to infinity, the clearance, Cmax, the half-life, and Tmax. I can see some difference between the two conditions for the half-life, the apparent clearance, and Cmax. However, the parameters also show large variability within each dietary condition. Next, I can apply a compartmental analysis to estimate a compartmental model and compare the estimated parameters across the two conditions. I choose a model with an oral administration, no delay, a first-order absorption, and one compartment and a linear elimination. Then I choose a weighting based on the predicted observations, which works quite well in many cases. And I find good initial values in check-init with the auto init button. And I set them as initial values. Then I run the CA. I can check the plot, in particular the individual fits, with the log scale. Here the parameters have been optimized independently on each individual and on each occasion. For example, here for the individual 1 in occasion 1 and in occasion 2. I can display the parameters with information. So for this simple analysis, PKanalix considers that the two occasions are independent for each individual. I notice that for some subject occasions, the absorption phase is not really well captured, like here for instance. So I choose a linked zoom on the x-axis to focus on the absorption phase for all plots. And this confirms that the absorption should be delayed in some cases, for instance here. Thus, I go back to the settings and I now choose a model with a lag time. Again, I can find a good initial value for the new parameter tlag with the auto init before running the CA. The individual fits are now quite good. On the plot of individual parameters versus covariates, I see that the estimated individual parameters show different distributions across the two conditions of diet, in particular for the absorption rate Ka, the volume V, and the elimination rate K. This suggests that there is an impact of diet on the PK of alcohol. But a detailed population approach in Monolix will give more precise results in several ways. First, the population approach in Monolix can take properly into account the variability between individuals and between occasions by estimating the parameters as distributions that vary at the individual or at the occasion level. Second, since the data size is small, it is not clear whether the differences that we see here are significant. In Monolix, I will be able to estimate the covariate effect and check if it improves the model. Moreover, the bioavailability is not explicitly taken into account by this model because it is not identifiable with only extravascular administration, so it is included in the apparent volume V. In Monolix, it is possible to use more complex models than the simple PK models from the library, and in particular to add the bioavailability explicitly, and it will allow me to assess in a more meaningful way whether guar gum could have an effect on the relative bioavailability depending on the value of diet. Therefore, I save and I export this model to Monolix. And I save the first Monolix project as run1. This opens a Monolix project in which the data here and the structural model are set up like in PKanalix. In statistical model and tasks, the individual model part is now split in two for the two levels of variability. The part on the left, at the ID level, describes the inter-individual variability, or IIV, and includes, by default, a random effect for each parameter. The part on the right is dedicated to the OC variability level, where it is possible to add random effects at the inter-occasion level to create inter-occasion variability, or IOV. Since diet varies from one occasion to another, it appears in this panel to explain part of the inter-occasion variability with a covariate effect. If I click on Formula, I see that the random effects are called eta ID, for instance, eta ID Ka for Ka. If I add a random effect at the OC level, the new random effect is called eta OC Ka. Let's briefly recall what is happening in such a case when we have both IIV and IOV. In the simple case with only inter-individual variability, for each individual I, the individual value Kai is modeled as the fixed effect Ka pop and a deviation from Ka pop based on the random effect eta Kai that is part of a normal distribution with standard deviation omega Ka. So all the individual values for Ka, for example for two individuals 1 and 2, are constant in time and part of the population distribution defined by Ka pop, the log transformation for Ka, and omega Ka. In case of occasions and inter-occasion variability, the model for Ka includes an additional random effect. So for each individual I and each occasion K, the value for Ka is defined by Ka pop, a deviation from Ka pop based on the IIV random effect for individual 1, and a deviation from this individual value for each subject occasion based on the IOV random effect, which is part of a normal distribution with standard deviation gamma Ka. So the distribution of Ka values across all subject occasions is a combination of these two distributions defined by Ka pop, omega Ka, and this one defined by gamma Ka. If the occasions are sequential in time, like here, for example, occasion 1, then occasion 2, Ka can now vary in time. But the occasions can also be encoded with overlapping times, like in this case study where they both start at time 0. The individual values Ka1 and Ka2 are part of this distribution, and an additional variability is brought around these values by this distribution to obtain the Ka values used in each occasion. It is important to note that the occasions are independent across individuals. This means that for both individuals 1 and 2, the model doesn't impose to have the same random effects for occasion 1. So these two deviations from the individual parameters are different, but they are drawn from the same distributions around Ka1 and Ka2. If the model includes a covariate that varies across occasions, like diet in this case study, with the parameter beta, the covariate effect explains part of the IOV. Here the difference in Ka between both occasions is explained in part by the covariate effect, which has an impact in the occasions where diet is not the reference category. The IOV distribution that explains this remaining deviation can now have a smaller standard deviation. After this recap on IOV, note finally that the boxes for adding covariate effect are grayed out when there is no inter-occasion variability. It is only possible to add covariate effects at the occasion levels on parameters that have inter-occasion variability with random effects at the occasion level, like Ka here, or parameters that have no random effects at both levels of variability. As a first step, I aim at validating the structural model without taking into account differences between the occasions. So I keep the statistical model to default with no IOV and no covariate effects. Then I select all tasks in the scenario, I save the project, and I run the scenario. First, I can check that all parameters have been estimated with a good confidence. This is the case except for omega Ka, which is small and with a high relative standard error. On the plot of observations versus predictions, the model does not show me specifications. In the individual fits, I see a fit for each subject occasion. I can disable the option Split Occasions in display to visualize the two occasions on the same plot for each individual. Moreover, I can color the observed data in Stratify by occasion or equivalently by diet. In this case, the predictions are identical for both occasions and they appear on top of each other, since no inter-occasion variability is taken into account in the model. The prediction curves are displayed in purple like usually for the first occasion and in orange for the second. By default, the curve for the first occasion is on top, except for the last individual, for which the second occasion is on top because it corresponds to a smaller observation period. I can see on this plot that capturing both occasions with the same prediction is not possible because there are small variations from one occasion to another, as I have seen during the data exploration. This corresponds to variability in the parameters between the occasions that can be taken into account in the statistical model and tasks tab by adding some random effects at the inter-occasion level or defining a covariate effect of diet. I will first focus on the random effects. Physiological considerations can help deciding if a parameter should have variability at each level or not. But in the absence of clear physiological knowledge, a possible approach is also to add a random effect at the occasion level on each parameter for which variability may be relevant, and check if the estimated standard deviation of the random effect is small. In this case, all parameters may show some inter-occasion variability. Indeed, the elimination rate can easily show some variations between different periods, and the dietary additive of guar might change the values of the parameters TLAG and Ka characterizing the absorption. The volume V is unlikely to vary much from one occasion to another. However, in this case, V corresponds to the apparent volume that includes the bioavailability of alcohol, which may vary with guar. Thus, I could set a random effect for IOV on V, or I can also modify the structural model to include explicitly the bioavailability and add the random effect at the occasion level on the bioavailability instead of the volume. This is what I am going to do. Before modifying the structural model, I use the last estimates as new initial values to facilitate the estimation for the next run. Then I open the structural model in the editor and I add an argument P equals F in the PK model macro. This means that the proportion of absorbed drug will be defined by the parameter F that I should also add in the input list. Here F is not the absolute bioavailability, which is not identifiable separately from V, but it is going to represent the relative bioavailability between occasions. I save this modified model under a new name and I check that there is no syntax error with the compile button. I can then load this new model instead of the previous one. After loading the model, Monolix brings me to the Check Initial Estimates tab to choose a good initial value for fpop. F is the relative bioavailability that can vary from one individual to the other, and fpop is its reference value, so I should fix it to 1. I can do this in the list of the initial estimates by changing the estimation method for fpop to fixed. Now that the model includes the relative bioavailability explicitly, I can consider IOV for F instead of for V. And I consider IOV for the other parameters as well. Since V and F are not identifiable together, I should not include IIV for F while there is already IIV for V. I save this project under the name run2 and I run all tasks. I can see on this plot that I now estimate the standard deviations of the random effects at the Hoc level that are called gamma. And I can see them in the table of population parameters. There are a few high relative standard errors for the standard deviations of the random effects because it is not possible to identify well all the random effects with such a small dataset. The random effects with the smallest standard deviations could probably be removed, such as omega Ka or gamma F, and we will see in a later step how to check more precisely which random effects should be removed. For now, I will first check the relationships between the random effect and the covariate diet. On the individual fit, there are now different individual predictions for each occasion. I can change the colors associated to each value of diet for the observations to match the color of the predictions. The predictions from equation 1 are in purple. They correspond to the first category, no guar, so I change this color to purple. The second category with guar corresponds to the second occasion with orange predictions. If I click on Information, the individual parameter values appear on the plots for each occasion. You can see that for V, which has only IIV, a single value is estimated for each individual across both occasions. For F, which has only IOV, a different value is estimated for each subject occasion. Indeed, as I have already mentioned, the estimated individual random effects from the distribution defined by gamma V are independent across IDs and occasions. I can see that the IOV allows to properly capture the observations for each subject occasion. In addition, the predicted alcohol concentration seems higher when individuals have taken guar gum, except for IDs 5 and 6. So we may be able to explain part of this variability with the covariate diet. Let's check this with the other diagnostic plots. First, the plot of individual parameters versus covariates can be used to compare the distributions of each parameter across the two occasions. Notable differences appear for Ka, K, and F. The kinetics with guar gum exhibit higher absorption rates and bioavailability and smaller elimination rates. I'm going to try to implement one or several of these differences in the model with a covariate effect, starting with the hypothesis that guar gum could affect the bioavailability of alcohol. The statistical tests in results show that these differences do not correspond to a significant correlation between eta Ka and diet, but there is a significant correlation with eta Ka and a slightly significant correlation with eta F. The lack of significance for Ka and F is explained by the small size of the data, which affects the p-values. Moreover, in addition to the tests, we should always keep in mind what is physiologically possible. And in this case, I follow the hypothesis that guar gum may affect the absorption or the bioavailability, and not the elimination. Second, I am going to have a look at the VPC that I need to add in the list of plots. And I split it by diet. Here, the prediction intervals are based on simulations that use the IOV included in the model, which is independent from diet. So the prediction intervals are almost identical on each plot, while the empirical curves differ with diet. With the 4 bins computed by default, empirical curves are well captured by the prediction intervals. So with this size of data, the small differences caused by guar gum do not cause a visible discrepancy of the model. But when setting the number of bins to 6, a small discrepancy appears in the absorption phase. Although I should keep in mind that the empirical percentiles represent only a small number of individuals, this is a hint that it could be relevant to take into account an effect of guar gum on the absorption or the bioavailability. As a result of this diagnosis, I can now adjust the model after using the last estimates as new initial values. Based on the diagnostic plots and the biological knowledge on possible mechanisms for the effects of guar gum, I will try to explain part of the IOV by adding a covariate effect of diet on F. I save this modified project as run 3 and I run all tasks. The new parameter beta f diet with guar is estimated to a small value, but with a quite good standard error. And it results in a small decrease of gamma f from 0.07 to 0.04. In the statistical test, I see that the p-value for the wall test, which checks whether the parameter is close to 0, is small, but the test is not quite significant. In addition, the correlation between f and diet is significant, and it is strong, as can be seen on the diagnostic plots. Therefore, the covariate effect is relevant and should not be removed from the model. Moreover, I can compare my different runs in Sycomore. I open Sycomore and I load the directory containing all the runs and I add them in the table. I sort by big and I see that the log likelihood and the big for run 03 are slightly smaller than for run 02, with 2 points of difference. So the modified model still captures the data as well as the previous run. Finally, in the next step, I am going to check more precisely whether I could remove some random effects that are not well estimated. To do this, for the next run, I am going to modify the settings of SAEM to disable the simulated annealing. This option is explained in details in our Feature of the Week video number 44. Briefly, it constrains the variance of the random effect to decrease slowly during the estimation in order to explore a large parameter space to avoid getting stuck in a local maximum. A side effect of the simulated annealing is that it may keep the standard deviations artificially high and prevent the identification of parameters for which the variability is in fact 0. This leads to large values in the standard errors. So when large standard errors are estimated for the random effects, like it is the case here, for example, for omega Ka and gamma f, it is recommended to disable the simulated annealing once the estimated parameters are close to the solution. Before changing the settings, I use the last estimates as new initial values to start really close to the solution. And then I disable the simulated annealing. I save the modified project as run 4 and I run SAEM. I can see in the graphical report that omega Ka and gamma f now decrease to a very small value. This confirms that there is not enough information in the data to identify distributions of values for Ka and f. I can check the very small values here. Therefore, I can use the last estimate and then remove the IIV on Ka and the IOV on f, while keeping the covariate effect of diet because f has no IIV. After doing this, I save as run 5 and I run the whole scenario again. All the parameters are now estimated with a quite good standard error considering the small size of the data. With the covariate effect of diet on f, the VPC split by diet, and with 6 bins, still show a discrepancy for the occasions with guar gum, but it is slightly smaller and it is likely due to the variability in the data. If I have a look at the plot individual parameters versus covariates, I see no more correlation between a parameter and diet. I can update my workflow in Sycomore to include the last runs in the table, and I can check that the BIC has not increased. So I consider this run, number 5, as the final model. Despite the small size of the data, it is able to take into account both inter-individual and inter-occasion variability, and to explain a modest part of the inter-occasion variability in bioavailability of alcohol by the effect of guar gum. You can also read this case study along with many others on our website. Have a good day!